And if you can get enough from the videos,
He got you then. So I was very confused. I thought the homework was due today, so I tried to do it last night.
Oh.
But I couldn't figure out the ones from 8.1. Like,
which ones?
I don't know.
Either of them?
Was a whole bunch of data. And I thought we just did like the expected observed.
Are all of
Yeah,
these in
that's
Excel?
what we do.
Oh, so I should have put. Okay.
Yeah, that's what we do.
So it's like the big table thing that we observed pieces in.
So, what number did I assign? So 12. Yeah, so you'll have to type in the data, which I know it's not necessarily the most fun, but so if you're going to do this with 10 classes of equal probability, remember that we can do that with, we're going to use the X bar and the S that they give us as estimates for the population mean and the population standard deviation. So if you want to figure out those classes and how many you would have equal probability, so each one has 10% chance of happening, we can use the normal inverse command. I don't want standard. The normal inverse will give us the boundary for a class. So if we go, sorry. Every time. R, there we go. Normal inverse. So the probability that we want, so we want to divide it into, the problem asks you to divide it into 10 classes of equal probability. So what you're looking for, of course, is you're trying to split up your x-axis into 10 pieces. And so the first piece will be negative infinity up to some point, and then point to point, and so on down the line to figure out what your classes are. So I need to figure out what the boundaries are for your endpoints, for your classes. So we'll do the normal inverse command. The first one we want is 10% cumulative probability. The mean, they tell you, is 511.633. The standard deviation, they tell you, is 87.576. So your left boundary would be 399. Okay, so then what you want to do with your boundaries is do that count if command to see how many, if you type in all your data, to count how many are in between each one. Remember doing those? Yeah. So that's the idea.
I think I got confused because like the example we did in class was like everything was 0 to 10.
Oh.
It was count if 0, count
if 1. Yeah, right. So this one, so the next one you would want to do is, say you wanted to do the next one for 0.2. I probably should have just typed these things in once instead of keep having to type them in over and over again because that's redundant. Okay. So if you wanted to, say, count the ones that are less than the 399, you would use that COUNTIF command. You would select your range, wherever that is. Wherever your data is that you've typed in, you would highlight the whole thing, and then you would absolute cell reference it so you can copy it down, right? And then you would say, in this case, what we want to do is less than. They're all whole numbers, and that's a decimal, so I can just use less than. If you wanted less than or equal to, you could type it an equal to next to it. Put the less than in quotes, and then use the ampersand and refer back to A1. So that will count everything that's in the array that I highlighted that's less than A1. I mean, in this case, it should tell me 0 because there's nothing in there. Okay. If I copy that down one cell, it will that will count everything that's less than A2, right? but that will include everything that's less than A1, right? So what I want to do is change that up a little bit and put in minus the one above it. So I'll change that over to A1. And then for that, then I can count down the rest of, or just copy it down, and I shouldn't have to change anything else.
Could you just put minus B1? Or would you have to do
I could, but then it won't work for the next one.
Oh.
Because it won't do cumulative at that point. You could do, this is probably just as easy. You could do the sum of D1 up until D1 and then absolute cell reference the first D1, or B1 I mean, and do the sum. You have to keep it cumulative though. You have to subtract them all off above it. If you just do minus B1, it won't subtract. When you copy the next time down, it'll only subtract off B2, not B2 and B1. So that was why. I think this way is just easier.
Yeah.
You see what I'm saying?
Yes.
Okay. Does that help, Haley?
Yeah.
Okay.
I had another question.
Okay.
On 8.5-12, they're not the same number of data.
Correct. They don't have to be.
Okay, so like, isn't that where you need to do the absolute value of the first column and the second column?
Remember that we're just trying to see if the median of the second one is less than the median of the first one, it looks like. So it says M48 is greater than M38.
Mm-hmm.
So when we do that one, I already have the data typed in this one, don't I? Okay. So this is my, it doesn't matter which one we go off of. They won't know if this one's bigger than that one, right? So this is the one where we want to rank all of them, but we only really care about the ranks of this column. So you can still do the same command. I can do rank I actually remember before somebody asked me to zoom in. Rank average. Why can I not do what I want to do today? Rank average of A1 compared to this. And then we want to do ascending order. That since Sid gave us the shortcut. Right? And all we care about is the ranks of the first column. So I can copy that.
Do we need to use like the sign thing?
We don't have to use this one. You want to use the sign thing because we use that different statistic for this one.
Okay.
We just have to do the sum of the ranks, and then we use that different expected value where we had the, what was it, N2 times N1 plus N2 plus 1 over 2, and then the N1. Yeah, you use those and do the normal distribution on that. So you don't have to worry about the signs in this case.
Okay.
Yeah. So you should just be able to do the sum of these and go on from there.
Okay.
You only have to absolutely make them. You only have to absolutely make them have the same length if you're doing paired differences.
Okay.
Because then you're trying to do the subtraction of the two and see if the median is 0 in that case.
I realize you shouldn't sign this, but we really don't care.
What am I doing? Oh, is this for Laura?
What? Yeah.
Is it? There you go.
Thank you.
Yep. Is that okay with everybody? Is that helpful to get you started on them? Okay. We did that one quickly at the end of class, so I'm fine with answering questions about that one, definitely. Any other questions? All right. Well, oh shoot. Let me go to my office. I forgot a handout I need to give today.
Yeah, that was when I was writing down the scope of the exercise. Drawing your own
Okay, cool. So, alright, question if I'm doing this right. So we're trying to do like.
Sorry about that. Good thing we're not that far from my office. So I'm going to go a little bit out of order than what our textbook does things for a couple of reasons. One, I think the order that I'm going to talk about things in makes a little bit more sense than the order that they're talking about it in our textbook. But two, this stuff's going to get hard pretty quickly, and I'm trying to put the easier stuff and this new stuff at the beginning for your next test, because your final is going to be take home. Right? So it's a little bit more difficult, and I don't have to worry about the time factor as far as that goes. Okay, so there's two reasons why I'm going to make things a little bit out of order and take a couple of things that aren't in the textbook as well. So trying to help things from both a testing standpoint and I think from a conceptual standpoint, I think it makes a little bit more sense. So
during finals week, you won't actually have to come in?
Correct.
Okay.
Yeah. And I'll give you your final sometime that last week of class. I mean, I'll actually hand out the take home the last week of class at some point. So
I was just because Dr. Olson was wondering about senior research.
Oh, right.
Presenting, so
Yeah, we won't have an in-class final for this or for numerical. They'll both be take home.
Okay.
Good. I don't think I could do well on an in-class.
So would the take home final be due the time that we would have our in-class final?
That'd be the plan, yeah.
It's on Wednesday, I think. Right?
Yeah, I think that is Wednesday, yes. Yeah, that would be what I would want to have to do. But I'll give it to you at least a week in advance. So probably more than that.
You're allowed to work together?
Was that? No.
I didn't think so.
No. Good question, but no. All right.
With you?
What's that?
Are we allowed to work?
You can ask me questions, yes. You're always allowed to ask me questions. All right, anyway. Let's talk about some more theoretical stuff. So the idea, well, yeah, this last part of the class is going to be highly conceptual over the stuff that we've been doing recently. I think the last stuff, while there's obviously some concepts that make the stuff work, and it's definitely very important to understand why the different hypothesis tests work, our focus has been more on actually running the hypothesis tests, right? So let's talk then about a little bit of theory. So we're going to be talking about a couple of different items of theory. We're going to be talking about theory of estimation a little bit, because we've already talked about that, and then the theory behind hypothesis testing in general, in particular focusing on power of a hypothesis test and understanding why power is a hard thing to get a handle on. We've already seen that a little bit, just trying to compute the power in pretty contrived scenarios, and then talk about how we try to control the power of a test when we don't have as much control over what the test is. So, of course, making a powerful test is important because, again, the power is related to the idea of committing a type 2 error with your hypothesis test, which, again, is not rejecting when you should. Okay, so that's you get to control very easily of rejecting when you shouldn't, right? But not rejecting when you should is harder to get a handle on. So that's what we're going to talk about. But this theory of estimation pops up in that idea. So I want to talk a little bit more about estimators versus the book just kind of jumps right into it, or your textbook jumps kind of right into it, and I want to at least get a little bit of an introduction into it, especially when we're talking about estimators in general. So the idea behind estimation, and we've talked about doing confidence intervals, and we've talked about maximum likelihood estimators. Again, the idea is to be able to take a sample from a population and use that sample in some way to give us an estimate for what the parameter is for the population that we're trying to test, whether that be the mean of the population, whether that's the proportion of the population, whether that's the variance of the population, any of those things, right? The idea behind it is you take a sample, you use that sample to get an estimate for the parameter. Now, it might be that you are assuming that the population is exponentially distributed, so the parameter you're trying to get a hold on is that theta. But again, we use the mean for the sample to give us an estimate for the mean of the theta, because the mean of the exponential distribution is the theta, right? So understanding estimators in general is important to be able to do this idea of fitting to distributions that you've talked about in Chapter 8, which is one of the things you have an assignment over, or being able to do hypothesis testing. Is this parameter really this value based on the sample that I got? Okay. So understanding these estimators is important. So there's all sorts of different concepts with estimators that we're going to talk about that I wanted to define and understand. So the first one is just the bias of an estimator. We've talked about this a little bit, but let's talk about it now in a little bit more precise idea. So, as far as the bias of an estimator goes, we say that the bias of an estimator for a parameter theta, so I'm going to use theta as the parameter, I'll put a hat on my theta to denote the estimator that we're using. The bias of that parameter, that estimator, is defined as the expected value of the estimator minus the actual parameter. Now again, this is the population parameter. So for a given population, it doesn't change. So as far as the the expected value is concerned, that's a constant that I underlined. And what's the expected value of a constant? The constant, right? So this is just the expected value of theta hat minus theta. Okay. So if the bias is 0, we say that theta is an unbiased estimator. Of theta. Otherwise, it's biased. We've seen lots of examples of estimators and trying to make them unbiased and those kinds of ideas. Probably the biggest one is the idea of using the sample variance as an estimator for the population variance, and why we divide by the n minus 1 rather than the n. Because the expected value, when we went through it, we got the expected value involved in minus 1 rather than n. So we had to divide by the n minus 1 so we could cancel that out. And that was all that idea of breaking it into pieces and looking at the chi-square pieces and all that stuff. I mean, it's been a while since we've done it, but we did all that stuff earlier this semester, right? But we had to, instead of using what you typically think of as variance and dividing by n, that gave us a biased estimator for the population variance. And to make it unbiased, we needed to divide by n minus 1 instead. And again, that was just the way that the chi-squared distribution worked out. But in general, for unbiased estimators, as an example, so let's let x1, x2, and xn be a random sample drawn from an exponential distribution. then theta hat equaling the sum of the x's over n is an unbiased estimator for theta, which here I'm using the theta as the parameter for the exponential distribution. The reason we know this, of course, is that the expected value of theta hat, in this case, would be the expected value of the sum of the x's over n. Well, n's just as far as this expectation is concerned, this n is a constant, right? So you get 1 over n, sum of the expectations of each of the x sub i's. But the x sub i's here are all coming from an exponential distribution with parameter theta. So what's the expected value for each x sub I? What is the mean of a exponential distribution? Theta, right? So each of these would just be theta. So you just get 1 over n times n theta, which gives you theta. Well, so if the expected value of theta hat is equal to theta, what's the bias? Yeah. We agree with that? What about, say, an estimate for the variance, for example? If I wanted an estimate for the variance here, well, what is the variance of an exponential distribution in terms of theta? Yeah, theta hat, it would be theta squared, right? So one thing that you might try as an estimator for theta would be, or the variance would be theta hat squared, right? Right, that'd be one thing you might want to try. So let me ask about, what about theta hat squared as an estimator for theta squared? So if I wanted to do the expected value of theta hat squared, well, I probably have to work a little bit harder at this one, because I don't think I necessarily want to square the square this thing and try to do it that way, right? So let's think about it in terms of how I can get at the expected value of a random variable squared without having to actually square it and go through it that way. We know that this should be the variance of theta hat plus the expected value of theta hat quantity squared, right? We agree with that? That's just rearranging our more useful formula for figuring out the variance, okay? We've already computed this. What is the expected value of theta hat? Theta, right? So this is variance of theta hat plus theta hat squared. Or not theta hat squared, just theta squared. I'm interested in the bias here. This is when I said, what about theta hat squared as an estimator for theta squared? I'm interested in the bias. If theta hat squared is going to be an unbiased estimator, if theta hat squared is going to be an unbiased estimator for theta squared, what's going to have to be true, looking at this formula? The variance would have to be 0, right? We agree with that? So this would say that for, and notice that this has nothing to do with the exponential distribution, by the way. This is a true statement, period. For theta hat squared to be an unbiased estimator for theta squared, assuming theta hat's unbiased, we would have to have that the variance of theta hat is 0. What's the likelihood of that happening? Well, think about what would have to happen in this particular scenario. Think about what would have to happen for your variance of your theta hat to be 0. It would be exactly the same as the mean. It would have to be the same number every single time, right? Remember, how did we construct our theta hat? You first took a random sample and then took its mean. What that would, for it to have absolutely no variance, that would mean that no matter what random sample you took, you would get the same mean every single time. Is that very likely? No. In fact, for a continuous distribution, now for any distribution, but for a continuous distribution, that's just impossible. Because if I take a random sample and take another random sample, the probability you're going to even get one value in common is 0, let alone all of them in common. Okay? So to have the exact same random sample come out as 0, now I know that you can get the same mean without having the same random sample. But the fact that to be able to get, when you're taking finite values to calculate a mean, and if you're doing a continuous distribution, the probability that you're going to get 2 random samples with the exact same mean is 0. It's just not going to happen. You've got way too many choices for the random sample. You're not going to get the same finite sum twice. It's not going to happen. Okay? So essentially what you can assume, I know what happens when you assume, but what you can assume, if you have an unbiased estimator for a parameter, its square will never be an unbiased estimator for the parameter square. So if you're trying to find an unbiased estimator for the variance for an exponential distribution, you can't just use the square of the theta that you use to find the mean, to estimate the mean. I mean, it's an estimator, it's just biased. So let's see if we can calculate the bias. Might as well, right? So what would the bias be? Well, I need to know what the variance of theta hat is. So the variance of theta hat would be the variance in the sum of the x of i's over n. That was how we estimated theta, right? What do you do with a constant when you move it out in front? Squared, good. 1 over n squared, variance of the sum of the x of i's. Now the x of i's are representing a random sample, right? Okay. So if we have the random sample here, those are all independent. So what can you do with variance over independent variables? Just add them up, right? Break it up over the sum, right? So this will be 1 over n squared sum of the variance of x of I. Right? And then each of the variances of the x of I is equal to It's exponential distribution in this case, so we're going back to the original example. Theta squared, good. So this will be n theta squared. So that'll be theta squared over n. All right, so if we calculate the bias then, okay, if we calculate the bias now, remember your bias is the expected value of theta hat squared minus theta squared in this case, right? The expected value of the estimator minus the actual thing that you're estimating. So we said the expected value of theta hat squared was theta squared plus its variance. And then we'll subtract off the theta squared. All this other work we did was all of this, right? So we just get theta squared over n. So we just calculated the bias for that estimator. Now, notice that as n gets large, what's going to happen to the bias? It gets smaller, right? In fact, as n goes to infinity, that limit would be 0, right? So we actually refer to this as what's called an asymptotically unbiased estimator. So as a definition, so let's let theta hat be an estimator of theta if the limit as n goes to infinity of theta of the bias in theta hat is equal to 0. We say that theta hat is an asymptotically unbiased estimator of theta. So in the example that we just did, theta hat squared was not an unbiased estimator. It was a biased estimator for theta squared. But it is an asymptotically unbiased estimator for theta squared because the bias went to 0 as n gets large. Does that make sense? At least as far as the definitions go. I know, lots of words today, and we're just getting started. We still have to talk about the concepts of consistency, efficiency, and sufficiency for estimators. Like I said, lots of words. Okay, so why I'm trying to start with the easier stuff for the exam, because I'd rather you fuss over the words on a take-home test than try to fuss over the words in a 2-hour exam. So anyway, let's do a couple of the problems that I made copies of here for you. So let's look at let's just look at the first example. The first exercise, 11-1. All right, so the problem's fairly simply stated, but you can imagine the scenario. You've got a random sample. that you're taking from some population, whatever that happens to be. Maybe you're doing trying to figure out a way to calculate a rate for a particular type of claim that you're trying to insure against. So you've got a bunch of data. You take a random sample from that data, and you calculate some statistic on it. In this particular problem, the statistic happens to be take the sample and add it together. Okay. You're assuming that the where you're taking the sample from is coming from a gamma distribution with those certain parameters. So you're assuming that you know the alpha parameter and don't know the theta parameter. And you want to calculate a C that's going to give you an unbiased estimator using your Y, how you get an unbiased estimator for the theta. So that's kind of the setup. All right. Okay, so the first thing that we need to do is figure out what the expected value of this Y is, right? Because the bias in an estimator is in terms of its expected value, right? We agree? So the first thing we need to compute here is what the expected value is for this Y. Well, the Y, again, is just the sum of the X's. And I know that expected value breaks up over sums. In a perfect world, we would want this to turn out to be theta, right? Because the bias will be 0. The statistic that we are using will be an unbiased estimator if the expected value of that statistic turns out to be the parameter, right? So in a perfect world, this would turn out to be theta, and we would be done, right? If it doesn't turn out to be theta, is when we're going to try to adjust it with a constant so that we actually get theta. That's the idea, okay? All right, so this is expected value of xi. What kind of distribution is the xi drawn from again? Gamma, right? The expected value of a gamma random variable is what? That's theta times alpha, right? And in this case, we know alpha is 4. So each of these expected values should be 4 theta, and we're adding it up how many times? 100? So this answer should be 400 theta. And again, that's because the expected value for a gamma random variable is alpha theta, and we're given that alpha is 4. So each of those x sub i's has an expected value of 4 alpha, and we're adding it up 100 times. All right? So we didn't get theta. We got 400 theta instead. So what constant would I need to put out in front of the y so that instead of being 400, I would have a 1? Yeah, 1 over 400, right? So we'll let c equal 1 over 400. Then the expected value of cy will just be theta. One over 400 is 0.0025, so the answer would be A in this case. Does that make sense? All right. So let's see if we can do 11-4. So looking at 11-4, what kind of a distribution are we looking at? In particular, that plus 4 weren't stuck in there. What kind of a distribution are you looking at? What is it? exponential, I agree, right? That's looks like a 1 over parameter e to the negative x over parameter, right? Okay. So if you're trying to estimate the parameter for an exponential, what do you typically use from your sample to estimate the parameter? The mean, right. And why do we typically use the mean to estimate the parameter for an exponential distribution? What's the mean equal to? Beta. It's equal to the parameter, right? The whole reason why we use, well, there's two reasons why. Actually, there's three reasons why. But the reason why we use the mean of the sample to give us an estimator for the theta is because A, the theta is the mean of the distribution. So just from an intuitive sense, it makes sense to use the mean of the sample to estimate the mean of the distribution. You do that if you've done that in any other statistics class that you've taken, right? Think about what you do for confidence intervals. When you do confidence intervals for the population mean, you use the sample mean and go left and right. Because as far as a point estimate goes, the best point estimate for the population mean is the sample mean. Right? Okay? So just intuitively, if the parameter gives me the mean, I'm going to use the mean of my sample to estimate the parameter. That's just intuitive. Okay? Now, what's the other two reasons? Well, number two is that mean happens to be unbiased. Using the sample mean happens to be unbiased. We did that up here. Right? When we did the expected value of the sample mean, we got the parameter, right? And in general, that works by central limit theorem, correct? The expected value of the sample means is the population mean. So if the parameter you're going for is the population mean, it's going to be unbiased if you use the sample mean, regardless. That's central limit theorem, right? Okay, so there's reason number two. One was intuitive, two is unbiased, three, it's also the maximum likelihood estimator. We did that back earlier this semester, right? That required a little bit more work. We had to do the likelihood function and maximize it. But the maximum likelihood estimator for the exponential is also the mean of the sample. So there's three reasons why we used it for exponential. And that's exactly what we have in this particular problem, right? It's exponential. Okay. So what we would anticipate using is we're going to let W bar just be the mean of the sample. Then what would the expected... Now, notice that this isn't written quite in terms of what we are used to for the exponential. What is the expected value of W bar then, in this case? For this particular distribution, what is the expected value? It's theta plus 4, right? Because the theta plus 4 is playing the role of the parameter, right? So the expected value of W bar would be theta plus 4. I don't want to use necessarily then just W bar to give me an estimate for theta. Notice I'm trying to get an unbiased estimate for theta. What would I need to do to get an unbiased estimate for theta? Remember, I want the expected value to end up being theta, so what would I need to do to get an unbiased estimate for theta? Yeah, just subtract the 4 over, right? So let's let y equal W bar minus 4. Then the expected value of y is going to be theta. So this would be your unbiased estimator of theta. Does that make sense? I want to emphasize again how we went through this to get to this point. Okay? Because notice that the problem didn't say using the sample mean, find an unbiased estimator. It literally just said find an unbiased estimator for theta, right? The reason why we chose the sample mean to start with is because we recognized the distribution as an exponential distribution. We know that the mean of the exponential distribution was a function of the parameter we wanted, right? And then the mean of the population mean is best estimated by using the sample mean. At least for our purposes right now. Unbiased was the best, is what I mean right now. We're going to have other ideas of what we mean by best later on. Okay. But that was why we started with the sample mean, calculated its expected value, and then adjusted it to get to the unbiased nature that we wanted. Does that make sense? Notice I'm trying to focus a lot more on the concept than the actual computing that we did. You okay with that? All right. We'll do more of this next time. We only have 2 minutes left anyway, so we'll do more of this next time. And we'll get, like I said, we're going to do some more definitions. We'll talk about consistency, efficiency, and sufficiency.